there. Our lesson today is fuels and energy. The applications of stoichiometry in combustion reactions. So, for fuels and energy, the objectives of this lesson are to, number one, to distinguish combustion reactions from other types of chemical reactions. Number two, write combustion reactions properly. And number three, to demonstrate the ability to solve problems involving the application of stoichiometry in combustion reaction. So what is combustion reaction? This involves the reaction of a material with oxygen to produce oxides of all other elements as products, releasing energy in the form of heat during the process. It is also commonly known as burning. If you would see this equation here, so we have here your fuel plus O2, it's pronounced as oxygen, equal to carbon dioxide or CO2 plus water or H2O. So it would be fuel plus oxygen would produce carbon dioxide and water. So this is the general equation for combustion. For fuels, these are normally made up of elements that readily react with oxygen, such as carbon and hydrogen. So example of these are butane, propane, and liquefied petroleum gas. So we have here an example. So this is your propane plus oxygen would form 3 carbon dioxide plus 4 water. So you have here your butane plus 5 moles of oxygen forming 3 moles of carbon dioxide and 4 moles of water. So you also have here your butane. You have, for every 2 moles of butane, you can produce plus 13 moles of oxygen. You will produce 8 mole of carbon dioxide plus 10 moles of water. So these are examples of combustion reactions. If you notice this, they have coefficients, and this would confer the law of conservation of mass, which states that matter can neither be created nor destroyed. So here you have there the reactants. In this table you have the reactants, and then you have the elements, and then you have the products, and then you have again on the other side you would see reactant, elements, and products. Okay, let's see first for the butane. Let's see first for the propane. So we have here 1 times 3 is equal to 3, and 5 times 2 equals to 10. 1 times 8 is equal to 8. So this corresponds for carbon. So carbon there, you only have 1 carbon from this reaction above. So you have C3H8, and then you have 5 oxygen there. So you would see there 1 times 3 coming from this here, the C3, and then we have oxygen is next. So oxygen, we have here 5 times 2 because we have there 5 O2, right? And then we have hydrogen as 1 times 8 because of the 8, because it's C3H8, so it's 1 times 8. So for the products, you would see there you have your carbon dioxide and water. So you have 3 CO2 plus 4 H2O. So if you would see there the CO2, the other side, the carbon is 3 times 1 equals to 3. And your oxygen your oxygen is 3 times 2 there from 3 CO2. So 3 times 2 plus 4 times 1 from the water. And then for hydrogen, you have 4 times 2. 4 times 2 there. Up. So both carbon is 3, oxygen both are 10, and hydrogen both are 8. So these are a balanced reaction. So at the same time with our butane, we have there 2 times 4 for carbon with equal to 8. And the other side, it is 8 times 1 equals to 8. So from this equation, you would see here, you have 2, see there, 2 times 4 for your carbon here. And you have here, on this side, is 8 from the CO2. And you have 13 times 2 for oxygen. This one is 13. So times 2. And then on the other side is 8 times 2 from the carbon dioxide plus 10 times 1 from the water. You add this. The sum of this is 26, so it's balanced. Then you have 2 times 10 for hydrogen. The 2 times 10 there. And then on the other side, you also have 10 times 2, so equal to 20. So this reaction is balanced. So it's very important for every reaction to be balanced. Okay, for you to better understand about the stoichiometry, let me give you an example. This is methane plus oxygen forming carbon dioxide and water. So you have here the molecule of methane, and then we have here 2 moles of oxygen forming carbon dioxide plus 2 moles of water. So what you have there in your left are called reactants. And what you see on your right is what we call products. If you would see there G, open parenthesis G, it means the state. G means gas. So if you would see there S, it means solid. If you would see L, it means liquid. So if you see there G, it means gas. If you would see there AQ, which means aqueous. And then the one in blue color is the coefficients. This is inserted to balance the equation. So we also have subscripts and coefficients which give different information. So for example, for your water, it's H2O, meaning 1 molecule of water, have 2 hydrogen atoms and 1 oxygen atom. If you have 2 H2O, which means we have 2 molecules of water, 4 H atoms, and 2 oxygen atoms. If we have H2O2, this is a different compound, which is 1 molecule of hydrogen peroxide, which means we have 2 hydrogen atoms and 2 oxygen atoms. So subscripts tell the number of atoms of each element in a molecule. Coefficients tell the number of molecules or compounds or moles in a given equation. So we have the different reaction types. We have here combustion reactions. This is when two or more substances react to form one product. Example here is given below. So you have, for example, you have nitrogen gas plus 3 molecules of hydrogen gas forming 2 molecules of ammonia gas. So this is another reaction. Then next, we have the composition reaction. This is when one substance breaks down into 2 or more substances. So if, example, you have calcium carbonate, which is your chalk. This is solid, forming calcium oxide, which is also solid, plus carbon dioxide gas. So this is an example of decomposition. So you would see here, next is the combustion reactions. This is our lesson, so which is the rapid reaction that have oxygen as reactant, sometimes produce a flame, and most often involve hydrocarbons reacting with oxygen in the air to produce carbon dioxide and water. So this is very important for your combustion reaction. So you would see there all the time carbon dioxide and water. But except for, if you would see there below, you also have your, if you have your hydrogen plus oxygen, since there's no carbon there, so you cannot produce carbon dioxide. But this is also a combustion reaction. Okay, for formula weight, we normally use AMU, atomic mass unit, or we also use molecular weight as gram per mole. So this is defined as 1/12 mass of the carbon-12 isotope. So 1 carbon-12 isotope would be equal to 12 atomic mass unit. So when it comes to formula weight, this is the sum of the atomic weights of the atoms in the chemical formula. So the formula weight of calcium chloride, for example, would be, for calcium, please check your periodic table. So you would have 40.01 atomic mass unit. And for chlorine, if you have CaCl2, note there that you have a subscript. So it's 2 times 35.5. So you sum it up. So you have 111.1 atomic mass unit. These are generally reported for ionic compounds. So for molecular weight, this is the sum of atomic weights of the atoms in a molecule. So for the molecule ethane, C2H6, the molecular weight would be carbon, which is, the coefficient is 2, so it's 2 times the atomic weight, which is the 12.0 atomic mass unit, plus hydrogen. So you have here C2H6, so you have 6 hydrogen times 1, which is the atomic weight or atomic mass unit of hydrogen. So you total this, will have 30 atomic mass unit. We can also compute for the percent composition, and one can find of the mass of a compound that comes from each of the elements of the compound by using this equation. So percent element would be equal to number of atoms times atomic weight divided by the formula weight of the compound times 100. So you can compute for percent composition by this equation. And for example, if you asked to get the formula weight of carbon, you can have there 2 times 12 atomic mass unit divided by the total of the molecular mass, which is 30, would be equal to 24 over 30 times 100, would be 80%. And hydrogen, percent hydrogen would be 6 times 1 divided by 30, equal to 6.06 atomic mass unit divided by 30 atomic mass unit times 100 will be equal to 20%.